Assalamualaikum. My name is Muhammad Faiz bin Mahassan. My mention number is 192483. I'm from New Hope Company. We have made a few changes for our process flow diagram. This is our latest process flow diagram. First, we have electrolyzer and then separator, followed by the compressor to increase the pressure. And then we have boiler to increase temperature before the product enter the reactor together with another in stream contain carbon dioxide. The product from the reactor will flow into our cooler and then to the reducing valve to reduce the pressure before going into the absorber, and then next to striper, and last one is distillation column. In total, we have 18 streams. The first unit for our process flow diagram is electrolyzer of water. The function of this electrolyzer is to electrolyze water to produce hydrogen. The process is a reactive process, and this is the chemical equation for this process. The temperature and pressure for inlet stream is 343 Kelvin and 1 atm, and the temperature and pressure for outlet stream is both 353 Kelvin and 1 atm. We choose T reference is for carbon, hydrogen and oxygen is 25 degrees Celsius and 1 atm. We assume kinetic energy, potential energy and work equal to 0. And to calculate the heat energy, we use heat formation technique, and the heat energy produced is positive, which is endothermic reaction. The second unit for our process flow diagram is gas-liquid separator. The function for gas-liquid separator is to separate water and hydrogen. The inlet temperature and pressure is 353 Kelvin and 1 atm, while the temperature and pressure for outlet stream, which is stream 4 and stream 5, is 353 Kelvin and 4.24 atm. The assumption that we have made is all the liquid exist at liquid stream. This whole process is unreactive process, and we choose T reference for this unit process is hydrogen and water at 80 degrees Celsius, 1 atm, and the heat energy produced is positive, which is also an endothermic reaction. I will explain about the compressor. So first of all, the function of the compressor is to increase the pressure. So this is our compressor. So the temperature from outlet to inlet are same, which is 80 degrees Celsius or 353 Kelvin. But the pressure changes from the 4.240 atm to the 30 degrees atm. So the mass balance from inlet, mass of inlet are equal to mass of outlet. But for energy balance, it is unreactive. So we assume that kinetic energy is 0, potential energy is 0, workflow is 0, Q energy is 0. But for the work shaft, we use formula which is mass of the flow rates times with specific changes of pressure over with specific gravity. For the specific gravity, we use hydrogen specific gravity, which is 0.070, and we have to convert it to its density, and by and then we calculate the work shaft in and we got isothermic. For the power, we divided the work shaft over with 3600 seconds. So we got the value is negative 1037708.431. Next, for our process flow diagram, we have boiler. The function of boiler is to increase temperature from 353 Kelvin to 533 Kelvin to enter our reactor. The pressure remains the same, which is 30 atm for stream 6 and 30 atm for stream 7. The assumption that we have made is the kinetic energy, potential energy, and also work done is equal to 0. And we choose the reference, which is hydrogen at 80 degrees Celsius and 30 atm and in gas state. The heat energy produced is equal to this, and since it is a positive value, therefore it is also an endothermic reaction.
Okay, hi, my name is Nofazahidayah and I'm a member from the Wood.Go company. So now I'm going to present to talk about the reactor system. So the function of reactor is to synthesize the methanol as the product, while the reaction between carbon dioxide and hydrogen gas, 3 mole of hydrogen gas, to produce methanol and water as the product. Okay, so basically the condition of the reactor system is 543 Kelvin and 30 atm pressure. So the phase for the input stream, which is hydrogen gas stream, the phase is in the gas phase, and also for the carbon dioxide input stream, also in the gas phase, and also for the product stream, which is the output, also in the gas phase. The condition at each stream for the both stream, which is stream hydrogen gas and stream carbon dioxide gas, the condition is same, which is 553 Kelvin and 30 atm. And for the output stream, the product stream, the pressure is same, which is 30 atm, and the difference is the temperature, is 543 Kelvin. So basically, to calculate the energy balance, we know that the reactor is reactive, so I'm using method heat of formation. So heat of formation is using elemental species as the reference. The reference is carbon, hydrogen gas and oxygen gas at 35 degrees Celsius and 1 atm. So basically, this is the table, the phase, and the mole, and the heat in and out, and also this is the table of heat of formation, and you can get this at table B2 in the textbook. So basically, this is the calculation for each species. To calculate this, I'm using this kind of formula, which the species which we don't have to calculate this is something. It already given in table B8. We're using this heat of formation plus sub in table B8 and plus this kind of formula. This formula is the real formula, which is to calculate the difference in pressure but in the gas phase. So the final energy balance we get is this. The Q, which is the heat in unit kilojoule per hour, we get this value 63808.0534.988, and the power in unit kilowatt, we get around this value. So this is the final energy balance we get.
For reducing valve, the function is to reduce the pressure. So this is our reducing valve. So the temperature for inlet and outlet doesn't change, but we reduce the pressure 30 atm to 1 atm. So for the mass balance, inlet mass flow rate for inlet are equal to the mass flow rate of outlet. But for the energy balance, it is unreactive. So we assume it is either gas, which is change of enthalpy is equal to 0, potential energy is equal to 0, kinetic energy is equal to 0. So Q equals to delta H, and H, the changes of in equals to changes of out. So this is our cooler. The function of the cooler is to reduce the temperature. So this is our cooler. So the temperature from inlet, which is 543 Kelvin, are being reduced to 343 Kelvin, and the pressure doesn't change. But some of the reactant for the inlet are in form of gas because it coming from the highest temperature, which is it come from our reactor. And after being reduced the temperature, some of the products are in form of liquid and gas, such as liquid and methanol. So for energy balance, it is unreactive. So we use reference point, which is come from our inlet, which is CO2, CO, H2, H2O, CaCOH, in form of gas, and 270 degrees Celsius and 30 degrees atm. And we assume that work is 0, kinetic energy is 0, potential energy is 0, and Q equals to delta H. And the boiling point of the water is 100 degrees Celsius, and for methanol is 64.70 degrees Celsius. And for heat vaporization, water is 40.656 kJ per mole, and methanol is 35.270 kJ per mole. We use C sub PDT to calculate the kilojoules per mole for the outlet energy. And this is our hypothetical path. And the energy that we produce is exothermic. Next, we have absorber. Function of absorber is to remove carbon dioxide, carbon monoxide, and hydrogen. The inlet temperature and pressure is 343 Kelvin and 1 atm, and the temperature and pressure for outlet stream is 323 Kelvin and 1. To calculate the heat energy produced, we choose our T reference, which is carbon dioxide in gas state, carbon monoxide in gas state, hydrogen gas in gas state, water in liquid state, methanol in liquid state, and MEA in liquid state at 73 degrees Celsius and 1 atm. And the heat energy produced is in negative value, indicate that the reaction is exothermic reaction. This is stripper. The function of the stripper is to remove CO2 and MEA. So the temperature for the stripper system is 323 Kelvin and 2 atm, and the pressure is 2 atm. So the phase, which is for our inlet, is in form of liquid and gas, and for our outlet, which contains of CO2 and MEA, is form of liquid and gas, and for the outlet stream, which contain some of the CO2 and H2O, CH2H, in form of liquid. So slipper is reactive, so we use inlet stream temperature and pressure as our reference point. Because of changes of the pressure, we have to use the real formula, which is AN plus 3PN over T square times with the changes of pressure. If the reactant in form of liquid or solid, we use V delta P, and we assume that kinetic energy is equal to 0, potential energy equal to 0, work equal to 0, and Q equals to delta H. And we calculate it. So we got endothermic reactions. Endothermic, which is the energy that we produce, is 33,333,681.279, and the power that we got is 92.689 kilowatt.
Okay, hi. This is our distillation column. So the distillation column is to get the light distillate and heavy distillate. Our product is in the vapor phase, which is the light distillate. The temperature that we assume that we set up is around 378 Kelvin and 2.245 atm, which is to get the purity, 80% purity methanol and 20% water. So we assume the pressure between bubble point and dew point to get those purity. And then for the energy balance, which is the reactive part, we use the reference, which is the input stream as the reference point at 50 degrees Celsius and 2 atm. So this is the Tref and Pref that we get at table. And the last one is the energy that we calculate, which is Q in unit kilojoule per hour, around 566.243087.354, and its power in unit kilowatt, 157,289.746 kilowatt. So that's all. Okay, this is our capital cost. Now, if you look here, we have 10 kind of reactor and 1 quantity for each unit. And for the overall total equipment cost, we got 734,499.71 ringgit Malaysia. And for the total ISBL plus OSBL, the value is around 420,089.692, and for the total investment required, we get 6279134.089 ringgit Malaysia. Okay, for the equipment part, we can see the cost of raw material for the carbon dioxide, the price is RM12 per ton. For the catalyst oxide, the price is 1,200 RM per ton. And for the price of water, we got 2.28 RM per ton. And for the MEA solvent, we got around 300 RM per ton. This is we got from Alibaba website. And for the electricity, TNB industrial tariff, we get this from the TNB website, and this is the reference. We got 0.337 RM per kilowatt hour. And here is the production rate for the methanol. The flow rate is this, and we convert to ton per year. And we get the price of methanol per ton around 158,000, and this is in the RM per year. So this is the total electricity cost that we calculate. We get around 35176232.72 ringgit Malaysia. Okay, next, this is our operating cost part. The operating cost consists of two parts, which is variable cost and fixed cost. Variable costs amount towards raw material and utilities, and the total for the variable cost is around 898 trillion, and for the fixed cost around 1 to 193,096 619 ringgit Malaysian. And so this is our table for the cash flow table with capital cost. You can see here, this is our cash flow and this is our revenue. So you can see here we get a positive profit. Okay, and the last one, this is our graph for payback period. As you can see, the first 3 years, which is 2 to 3 years, the value is constant, is fixed, and then it's rise until the end of year, the value increase. And okay, that's all for our costing. Thank you.